Okay, let's unpack this. Math and food security. It might sound like an unexpected combination.
Yeah, definitely. But the sources we're looking at for this deep dive, they go right there.
Hmm.
What's fascinating here is our material focuses squarely on math differentiation in food security. So it's zeroing in on how temperature affects enzyme activity,
Okay.
and crucially, how math, helps us understand all that.
And the sources didn't just mention the connection. They really got into the specifics, didn't
I
they?
know.
Things like differentiation and integration.
Exactly.
Mhm.
Right. So our mission today really is to pull out the most important bits from these sources. We want to show you how these seemingly abstract math ideas tie directly into something as critical as keeping food safe.
And, understanding its shelf life.
Precisely.
It's definitely not the first place you'd think calculus pops up.
Not at all. But the source material, it makes a really compelling case. It points directly to how those temperature changes impact enzyme activity.
Uh-huh. That biological machinery driving, everything from ripening to spoilage.
Right. And that's the key area where differentiation and integration aren't just relevant, they're essential according to these sources.
So it raises this important question then.
Hmm.
How does the rate at which enzymes kick in, or maybe shut down, as
Yeah.
temperature shifts,
Which is exactly what differentiation helps us analyze, yeah.
how does that inform, say, food safety decisions? The sources actually dive into modeling that rate of change.
They do. And it's not just about the rate at one specific moment either.
No.
The sources also show how integration, thinking about the total effect or the accumulation over time becomes absolutely crucial.
Okay, think about food maybe going through different temperatures during transport or storage.
Exactly that. The material highlighted how differentiating the function that describes enzyme activity, with respect to temperature,
Hmm.
it lets you find critical points.
Critical points like,
Well, for instance, one source showed how this math could pinpoint the exact temperature threshold where a specific spoilage enzyme's activity just takes off, accelerates most rapidly.
wow, okay. So knowing that precise point is vital for setting storage standards, right?
Absolutely vital.
That's where it gets really interesting because it's not just warmer means faster spoilage. The map helps identify these nonlinear relationships, tipping points you might not spot otherwise.
Yeah, exactly. The sources gave examples where the rate of change of spoilage wasn't constant at all.
And differentiation was the tool needed to actually understand that pattern.
That's the one.
Yeah.
And then, okay, there's integration.
Right, the cumulative side.
The sources looked at scenarios where, instead of just one steady temperature, food experiences ups and downs.
Fluctuations.
Right, so integrating the enzyme activity function over that specific temperature profile for a whole journey, maybe, or a storage period, allowed them to calculate the cumulative enzyme effect.
So it's like getting a kind of total enzyme damage score over time, not just looking at the peaks.
You got it. And the material demonstrated how this cumulative score, which you get through integration, gives a much more accurate prediction of a food product's actual shelf life.
Better than just using, say, the average temperature.
Much better, yeah. Because the average can hide damaging extremes.
Makes sense. So if we connect this to the bigger picture,
Right.
managing global food security, that needs really precise prediction, precise control.
Especially across diverse, often unpredictable environmental conditions, yeah.
So these sources frame these mathematical tools, differentiation for rates and thresholds, integration for the total impact as basically fundamental.
Fundamental for building robust models,
Yeah.
yeah. Models for predicting how food quality and safety might degrade over time.
It really shows how these concepts, the ones you might see as abstract in a math class,
Uh-huh.
they have incredibly tangible, high-stakes applications out here in the real world, directly influencing things like food waste, public health.
By improving those shelf life predictions and storage recommendations,
Yeah.
it makes it crystal clear that understanding change and its total effect isn't just academic.
Yeah, so it's a powerful tool.
A really powerful tool for solving these complex biological and logistical challenges in the whole food supply chain.
So wrapping up, what does this all mean? We've taken a quick look at how these sources connect mathematical ideas, differentiation, integration directly to practical stuff.
Like understanding and predicting temperature's impact on enzymes for food security.
Yeah. It's fascinating how these tools are used to tackle such critical real-world problems, which kind of raises an important question, doesn't it?
Mm-hmm.
Beyond just enzymes and temperature. How else might understanding rates of change and cumulative effects, through differentiation and integration, be silently shaping other parts of our world we don't even think about?